So yeah, we now have the RISC Zero workshop. The workshop is called Get Rusty with RISC Zero. Build your first, oh, no, maybe not first. Build your ZK Rust application. All right, very cool. Take it away then.
Okay, so hello everyone, and welcome to ZK RISC Zero workshop. Get Rusty with RISC Zero and build your ZK Rust application. So today we have present our CEO, Brian Retford. He will be presenting with us. Hi, Brian. Then I will be doing a bit more, I will continue a bit more of a workshop, and then Hans, our solutions engineer, will present our latest Bonsai demo, Bonsai Pay. So after Brian presents a bit of like his part, there will be a Q&A session with Brian. But let's first see what we are covering today. What's our plan? So we start with introduction to RISC Zero, and then we'll be looking at the two products, RISC Zero products, ZKVM and Bonsai. We'll start with ZKVM. We'll go through ZKVM architecture. Then there will be a Q&A session with Brian. Then we'll go through, I will run you through RISC Zero terminology, and we'll look at the kind of most exciting features of ZKVM and things that make RISC Zero ZKVM stand out across different available zero-knowledge virtual machines. Then we have architecture overview of our proof systems. We'll go through a quick start. So I want to make sure that you guys who are our audience developers ready to start building. So after this quick start, everyone will run our ZKVM, and then they will generate a proof, zero-knowledge proof on it. Then we have a break in around like 45 minutes. And then we'll dive into Bonsai, our ZK proving service, look what it is and why we need it and when is it to use it. And we go through Bonsai Pay walkthrough with Hans. So after each section, I will pause for a bit and have a quick look at the chat to make sure that all questions are answered. But if there is some questions get too specific, I won't read them loudly. I will reply later through ZK Hive Discord channel, or one of my colleagues, Paul, our ZK researcher, or Hans, they will be helping also answering questions. So and now please welcome Brian, our CEO and co-founder of RISC Zero.
Thanks, Iryna. Thanks for putting this workshop together. Really excited to get into it. All right, so RISC Zero, when were we started? We were started in 2021, and I guess from our perspective, we're focused on revolutionizing the internet by creating like the infrastructure and tooling necessary for Web3 developers around the globe to build zero-knowledge software. We're doing this by bringing general-purpose computing to the zero-knowledge ecosystem, which enables users to trust programs run anywhere while allowing developers to use the tools they already know and love. So while this is true, it's not technically true. We actually started in about 2020, and we started, we started by building building a proving system sort of from the ground up, and then writing a bunch of circuits, which we all know is very fun, but also extraordinarily difficult and kind of hard to maintain. So while we were, experimenting with ZK, we came up with this notion that wouldn't it be great, to program a ZK system if you could actually just program it like any other microprocessor. So this is how we got into RISC Zero and how we decided to create this general purpose ZKVM. Next slide. So what does it even mean, I guess, to have a general purpose ZKVM, and what, how does RISC Zero approach that? So we took the open source RISC-V microarchitecture, which was developed by a bunch of different teams out of Berkeley and the company Sci-Fi, and it's still very actively used, and RISC-V cores are actually showing up in all kinds of hardware in pretty much any system that you're going to buy these days. There are little RISC-V cores everywhere. So RISC-V itself is like ARM or like x86. It's a description of how to program a computer in a way that you can run any program. So the circuit that RISC Zero actually represents, we actually have several circuits, but the main one is this ZKVM. So it's a circuit that takes RISC-V instructions and proves the execution of them in zero knowledge. And it does this by using a ZK Stark-based system. So run the same circuit over and over and over again and build up this kind of trace over time that when it's complete and you actually prove the entire trace, you're proving the correct execution of this RISC-V program. I don't think we get into it too much, but we do also have these sort of accelerator circuits, which are useful and necessary for things like cryptographic operations, such as hashing and various signature algorithms. Yeah, next slide. So what does using the ZKVM look like? It actually, you write regular Rust code. There's a certain way that we tend to structure it. So there's a host and a guest, and I think Iryna will get into all of that. But it really is just Rust code, and a standard compiler produces something called an ELF. This is just a way of wrapping executable code and containing it in a format that operating systems are able to interpret and load. So you can think of the ZKVM as its own little computer, and it loads this ELF binary into an executor, which actually runs the program, figures out what should happen, and creates this log that can then be sent to the prover, which then proves it and creates this succinct receipt that you can then post on a blockchain or do anything else you want to do with it. Yeah, next slide. Okay, this is slightly different than the one online that I saw earlier, but that's fine. So yeah, but why is this important, and what can it do? General purpose ZK is important because honestly, like maintaining complex sets of circuits for complex state machines over a very long period of time is very expensive and incredibly difficult. Now, it might make sense to do this, but for certain systems, but we tend to think that it makes the most sense to focus, for developers to focus on the actual state machines and the programs they're trying to prove. I think the work that we did with Zeth and that we're continuing to do with Optimism really highlights this. We took an entire EVM that was largely coded by other people, modified it slightly, and then we're able to prove we're able to create a full type 0 ZK EVM in just under a month. And this approach actually lets people modify the EVM and continue to create validity proofs for it without needing to go back and reconstruct a bunch of circuits to create some modifications. So I really see general purpose ZK as creating a massively lower barrier of entry for developers in this space, and not just barrier of entry, but also decreasing the full cost of building innovative ZK systems over a very long period of time. So really, the ZKVM lets you create programs that are maintainable and prove them in ZK easily and quickly.
So now there is opportunity for anyone to ask questions on the chat or on Q&A. Ask questions to our CEO, Brian.
Yeah, so we can go in order here. Let's see. Yeah, so how is correct memory access proven? There's a talk from ZK Summit 9, I think, might be 8, where we actually go into this, and there's some material on our website, but it's actually pretty it's a pretty long discussion, but there's a lot of material about that. It's pretty interesting, and it's actually, I would say, an active area of research. Everybody approaches it differently. I think our next version of the circuit approaches it slightly differently, and how exactly that works actually gets into this sort of continuation system that we have, which lets a program be split up into many, many chunks that can all be proven in parallel. Cool. Is the VM stateless, more like a coprocessor? So I would say the VM is not stateless, but you pass the state into it. So in the context of building, say you wanted to build a ZKVM L2, the state would live, on a blockchain as it normally does. But then when you go to prove something, you pass your inputs in and you get an output back. So I guess in a sense, it's stateless. Like, we don't currently have a system that we provide to people to maintain state between executions of the ZKVM. Although there's a lot of really exciting possibilities there, and I wouldn't be surprised if we, eventually do release something that makes more stateful programming simpler, if that makes sense. Let's see. Do I understand correctly? The ZK part of a calculation, FA equals B equals A plus A, return B. Can F at A and the public / shared part can be A? I think that an amazing thing about ZK is that you can actually, you can decide to share any of the inputs, the outputs, or the program, or you can choose to conceal all of those as long as you have a consistent way to build the program and communicate with other people what the program is supposed to do. So really, you can any part of it can be public, any part of it can be private. See, do we consider to create a sort of proof generation layer to interact with? So that's what Bonsai is. We'll be talking about it later. Are there any future plans for enhancing the RISC Zero proving system, such as incorporating alternative systems like Snark, Lasso, and Jolt, or others? Indeed, we're constantly working on improving the proving system. The current next version of the circuit, we will be releasing as soon as it's stable enough to do that. And it's quite a major leap forward and has an entire compiler infrastructure. And it will be easier to incorporate different sort of lookup techniques. I will say that we already sort of incorporate alternative systems like Snarks in a sense. You can actually take any of our Starks and sort of exchange the Stark for a Groth16 proof that you can post to Ethereum. So I think we also cover that in a little bit. Let's see. Yes, a circuit is always finite. However, the runtime of a normal program is not known a priori. How do you solve this? Well, yes, circuits are always finite, but the way it interacts with the input to the circuit is the actual set of instructions. And eventually it terminates or not. If it never terminates, obviously you can't create a proof of it not terminating. That's what I would say. Is there a known protocol and tooling to upgrade the ZK part of the proof to say? I don't think so exactly. If you're trying to say, if you're trying to reference a prior program and say this next program sort of, I'm not sure exactly what that question is. But if you can clarify, maybe we can answer more in more detail later. Let's see. Are there efficiency trade-offs for using general purpose ZKVM on different blockchains? There's always efficiency trade-offs, I think, in every ZK proving system. And, it really depends on the use case and what you're doing and how much efficiency matters and all kinds of different things. So yes, there are trade-offs. Why the choice of Stark? Starks are very good at running the same sort of circuit over and over again. So basically, they're most efficient for ZKVMs, and we're primarily a ZKVM. Let's see. Why did we decide to use a smaller field? So I think we were sort of pioneers in using the baby bear, like sub 32-bit fields. It's actually, the RISC-V ISA, there's 64-bit versions and 32-bit versions. We support the 32-bit version, but the reason we focused on the smaller field is because we were focused on GPU acceleration and basically being able to fit everything inside 32 bits is usually a win on a GPU. Yeah, I think RISC Zero is not aimed as a replacement to the EVM, and I think Zeth is a really good example. Sorry, the question was, is RISC Zero aimed as a VM on ETH L2s as a replacement to the EVM? I think we'll see people using it to add general purpose functionality to Ethereum, but also we'll see people using it for co-processing and other applications that very much are, you know, the EVM. Let's see. Is it possible to use the ZKVM of RISC Zero in a small embedded system? I mean, possible, yes. Practical is really going to depend on your use case. I, for one, would love to see like a small device that would let you scan one's passport and sort of print out a QR code that you could scan and get like a proof, redacted proof of something from your passport, and it just have that program live on a tiny microcontroller. And that's probably possible because the latency demands are not super crazy. Let's see, Thor, what applications outside of blockchain are you interested in for the RISC Zero VM? It's interesting because I think blockchain can apply to so many different things. Generally speaking, the thing that I get most excited about these days is the combination of ZK identity for anti-Sybil, or let's just say like being able to create a service with a set of users that it's much harder for people to sort of abuse the service, and utilize the capability of ZK to let people, you know, prove the correct execution of programs to create, I guess, I always think of it as like a public AWS or a cloud where people can actually create programs and have the programs kind of pay for themselves indefinitely. So I saw there's some article in Hacker News that Jeremy forwarded me where somebody was lamenting that, you know, you can't, everybody's into like baking sourdough bread, but like making an app and having it exist in the same kind of context as that doesn't really work out. So I don't know, that's something I'm really excited about in the future. Yes, basic full stack applications. I will let the solutions engineering people answer that. We certainly have examples that show how to do that, and then we have some full stack applications. But the full stack application, I think, like Bonsai Pay, is a bit more involved. Is it feasible to develop a privacy-preserving machine learning library utilizing RISC Zero? Certainly possible, feasible. I think that's, it seems like we're a couple of years off from those things being feasible, in my mind, period. Yeah. Can RISC Zero used to compress previous state such? Can RISC Zero be used to compress previous state such that the size of a node is reduced? I think the answer is yes. I don't think we will be sketching the sort of exchange between a consumer and user and the ZK provider. The Bonsai Pay example actually goes through a lot of that, actually. So yeah, maybe we will be. Let's see. So many questions. I love it. How does it compare to a T? Very different from a T in the sense that, you know, the ZKVM doesn't guarantee privacy from the party executing the transaction. It can produce a proof of correct execution that masks inputs, but the person executing the proof will always have access to the sort of state of the program and the inputs. So I actually think T's and ZK are totally complementary. I think Scroll just maybe put out a post about that a second ago. So running ZK things inside a T is just a way to add, well, lets you add the privacy component in, but it gives you this sort of portable proof of correctness that's not dependent on centralized signature signing authorities like T's are, and not as compromisable over the long term, I think. Thor asked, to what degree do we believe, or do I believe, that all Stark VM designs will converge on a relatively similar architecture? I don't know, is my answer. I think there's probably room for them to be different, but I think the tools in which people use to create these kind of things will probably converge over time. That's my guess. Yes, can RISC Zero be used to create workflows on-chain with privacy, where some of the components are private and some of the execution is public? The answer is yes, but you kind of have to, getting back into this like T example, you'd want to run the private part either in a T or locally or via a sort of trusted proof provider that doesn't keep logs of everything, like Bonsai. I think ZK identity, I would love to. I think we'll probably have to save that for a different time, or actually Bonsai Pay gets into it a little bit. Which benchmarks do we care most about when comparing ZKVMs? That's a good question. We've decided that we care the most about real world benchmarks. Sadly, we haven't, I don't think we've settled on a set of use cases that are that are most representative of what's interesting in the real world. I think we're starting to see the kinds of things that are like verifying JOTs. We'll get into that with Bonsai Pay, and then obviously, building Merkle trees and things like that. But there's probably a lot more, and I think that would be a fun thing for industry collectively to kind of, agree on, so we could start thinking about comparing ZKVMs in a saner way. All right, is RISC Zero mainly aimed at generic off-chain execution and proving on-chain? I mean, that's certainly something you can do with it, and we're building tooling to make that easier. But I think getting back to the start, it's really aimed at being a truly generic ZK proving system. Do we integrate with any proof acceleration systems as a service? Currently, yes, that would be Bonsai, which we built ourselves. We will almost certainly be integrating with other people's systems and also extending the set of people who can run nodes for Bonsai in the future. So let's see. You mentioned RISC-V chips, but can you run a RISC Zero program on a computer with an ARM? Yes, it's just a VM. So just like you can sort of run an x86 program on an M2 MacBook, or you can emulate ARM for mobile development. You can run a RISC Zero program on any architecture that it compiles on. And then, all right, last easy question. Will you all be at ETH Denver? Many of us will, yes. I'm excited to go back to the rodeo there. Cool. Thanks for all the questions.
Thank you so much, Brian. It was super, super great. Thank you. So I will continue with the terminology. But I believe Brian will be still here, so feel free to ask questions. There is my colleagues there. There is Paul and Hans who will be answering questions as well. So let's move to the terminology. Sorry. So Brian just went through ZKVM architecture, but let's look how we call it within RISC Zero. So we have a guest is a program that is running inside ZKVM. So this is actually that input program that you as a user send to the ZKVM. And we also have a host. So host is a system that runs ZKVM, and host emulates the guest. So it like reproduces the program. And then we have a prover. So prover is the portion of ZKVM that verifies the correct execution and then approves this guest program. So it constructs the proof. And it also constructs the receipt. So let's look again at this like ZKVM architecture. So here we have this like guest code. This is this program that you send to the ZKVM. This is what you want to prove. And proof of this guest code will be generated. So this is your Rust code. So then you got this, it will be run on the compiler and generated executable ELF binary for you. And this is the host. So this is where you run ZKVM. And this part is a prover, so it validates and proves a guest program and constructs the receipt. And what you get out of ZKVM is a receipt that attests the valid execution. This is evidence of valid execution of guest program. How we do it? So we have this like host, and host emulates the guest and sends private data to the guest to the ZK circuit, and then ZK circuit execute code and commits the result to receipt. Receipt returned back to the host as a proof of the computation, and then host can like forwards this receipt to verifier for checks. So receipt, receipt contains like two parts. This is like receipt that validates the execution. It has a journal, the portion of receipt that contains like public output of ZK of this program that you sent this like guest program that you sent to ZKVM, and the seal. Seal is the portion of receipt that cryptographically attests the correction execution of the guest program. So basically, seal is ZK Stark proof and is generated by this prover. So receipt has like two parts, like journal, which is like public output. So yeah, be very careful what you commit to journal, because it will be available to everyone who has a receipt. And then seal, this zero knowledge proof. So basically it's a collection of hashes. And yeah, so this is our terminology. So we have a guest that this is the program that you run, you send to ZKVM to run and to validate and create ZK proof of, and you have a host. The host actually like runs ZKVM, and also sends private data to ZKVM, and this, and then there is a receipt, and that is the object that contains ZK proof of the correct execution of running guest of your program, and which is a journal and a seal. So this is a couple of main terminologies and definitions that we're going to use through this workshop. So let's look a bit like under the hood. So what's in the receipt? So this is like ZK Stark this is the part that is a seal, like the ZK Stark. So since so Brian mentioned that we use ZK Starks, and The prove and verifier, so we use like Fry algorithm and Deep Ali with a Fiat-Shamir heuristic. And to prove, verify that execution trace satisfy these appropriate constraints. And this is execution trace. Execution trace, this is happening within ZKVM. This is like when the guest program, the RISC code that you sent to ZKVM has been like executed, and then this is basically a table of states. So each row represents a clock cycle, and each column represents a register. And then this execution trace is sent as input to the prover, and prover proves that it's been that's been run correctly. So if we only needed to prove and check the correct execution, then we would be enough. But we also need to generate a zero knowledge proof. So that's where we need to go a bit like further. So we have this like trace as a witness. So so we have to make sure that the initial state matches claim code, the results claimed, and there is a computational integrity. So each step must be what RISC-V processor would be. And we encode the trace algebraically. So so to make sure that the conditions become algebraic constraints, and encode trace is a witness. So another part that we wanted to go over is our new features that have been released last year, and we are super excited about it. And this is continuations, and this is something that no one else actually has within their VMs. Within the ZKVM, so nobody else generated continuations. So it means that nobody else can generate proofs on like parallel clusters. So before continuations came around, there was sometimes like limit how large was your program that you can send to ZKVM to validate and to generate a ZK proof. And so now with the ZK with this continuations, it means that we can do we can produce a proof of very large program. And the biggest that is done is 1 billion cycles. So, but basically it's like how long our engineers can wait on a proof. And so before continuations, the maximum proof size was 16 million cycles. And now after continuations, it's around like 10 billion cycles, and this is that nobody else is doing, like the parallel proving. And this is by far the biggest differentiator of RISC Zero ZKVM in comparison with others on the market. So you can actually delegate generating proofs, and it's like really, really fast. So so yeah, this is very exciting, and this opens quite large new use cases that were not available before. So it's so this is the main our differentiate and main advantage of ZKVMs and Bonsai. So now we have continuations, and also we can optimize our proofs to make it small, to have it on chain. Just like in a second, you'll see how we do it. And yeah, so now all the pieces of our systems are in place. So it's you can take very large RISC program and run it and generate ZK proof. You can also validate it on chain, and we also introduced Docker that to make sure that you can run deterministic compilations, and introduction of continuations just make and Bonsai just like make the whole system like faster and allows very, very large programs to be used as an input to ZKVM and to generate ZK proofs of very, very large programs. So so this is now we have 10 billion cycles, but theoretical maximum is around like 100 trillion. But this is the largest that we run, and very exciting times for sure. So let's go into our proof systems and learn a bit about what it is and architecture of our proof systems. So the architecture of our proving system at RISC Zero is very, very similar to architectures of several other mature ZKVMs. Plus, we have continuations, which means that you can generate ZK proofs at very high speed, and you can generate ZK proofs of very large programs and code. But our so it's very similar to Polygon and ZK Sync, but we have our advantages. So let's look closer what's ZKVM. So in a normal virtual machine, there is a process where you send program as an input, and you send input data for this program. You send these two input parameters, program and input data, to the VM. And VM runs it on this data, input data, and generate output. So all is correct. But for ZKVM, it's very, very similar setup. So you have input program that you want to run, emulate on ZKVM, and you also send input data for this program. And ZKVM runs it for you and produces not only output, but also proof of running this this program on this data. So there is a proof of correct execution. And this output, or like journal and proof as a seal, is inside one object that we call the receipt. And so this is very similar to virtual machines, to general virtual machines. And if you look closely to RISC Zero, it's already like very generic because you can submit programs in Rust. So this is also quite an advantage in comparison with other zero-knowledge virtual machines. So let's look at the recursive proving that we have. So recursive proving is when you take several proofs and ZK proofs and compress them into a single proof. So you aggregate proofs into a single proof. And these orange objects on the slide is a receipt, right? So on the first layer here, there are like 4 receipts that have been generated by RISC-V circuit, right? So 4 proofs, and we take 2 of these receipts and use them as the input for our recursion circuit, right? And they produce another receipt. So you take 4 receipts and you send them as input to recursion circuit, and you have output as one receipt. So this way we can use a recursion to compress any amount of proofs into a single proof. And note that the initial receipts here, they came from RISC-V circuit, and they're actually like 2 stack circuits here, right? So RISC-V is like our initial circuit that generates our proof of RISC-V execution, and then there is a separate recursion circuit that we use to compress our proofs, our ZK Stark proofs. And at the end, it compresses into one Stark proof. So this is a diagram of a single proof of RISC-V circuit, and this is the executor, and this is part is a prover. That's if you remember what Brian explained, like at high-level ZKVM architecture. So executor takes trace from the binary and generates and it's being like split into several kind of parts, and each part sent to the prover to generate RISC-V prover to generate the Stark proof, right? So we generate like several receipts, and then we use a recursion to compress those receipts into a single receipt. And then finally, we use growth 16 circuit to compress our receipt, our Stark receipt, into something small enough that can be verified on chain. So we use Starks for all of these proofs for the RISC-V prover, and for recursion circuit we use Starks. And the proof size for Starks in our system is around 250 kilobytes. So the gas cost would be too large to verify it on chain. So that's why we added one more circuit here, growth 16 circuit, to our stack, which is a snark wrapper. And this growth 16 circuit produces like very tiny, very little proof, which is like snark proof. So there are like few layers of proving. So we have initially we run proofs to generate these 6 receipts using RISC-V, right? So and we also use Fry for those proofs. So Fry is a proof system that's very efficient for the recursion. And then we do recursion. So we aggregate those receipts into a single receipt. All those like Stark receipt into single receipt. And then we use growth 16 circuit to generate a very small proof. So every recursive recursion circuit takes 250 kilobyte Stark receipt. So since it takes 2 receipts, it means that it has it takes half a megabyte, and then produces one single 250 kilobyte receipt. And our snark receipt is 100 bytes, so it's quite a difference. And so that's how we generate this this snark receipt. So also want to come back to the recursion that we use. One second. So here you see that we split our execution trace into several segments, and we prove each of these segments, right? So because of the these continuations that are available now, how we do it, we actually prove that each of these segments in parallel. So rather than proving generate ZK Stark proof for 1 billion cycles of like of a large program, we get proof for each of these segments, and then we input these proofs into a recursion. And in order to compress those proofs, we use growth 16 circuit for single receipt to generate a single snark circuit. So if you want to learn a bit more about our proof, about our proof systems and considerations that drove our ZK researchers and architecture decisions, I would highly recommend you watching Paul's presentation on approved systems. So you can find it here, and I will post it in the chat. And yeah, so this is in-depth discussion around our proof systems, around decentralization, and how these can be scaled horizontally, and how long will it take to compute each proof. And yeah, so I think there is one receipt is missing. So there's supposed to be another circuit, recursion circuit here, and then it generates receipt. It goes into this recursive circuit. So, but do please watch Paul's presentation. So, and yeah, we now will move to example walkthrough of factors, but let me check first the questions to make sure that we are.
Hey, Iryna, I'm also going to jump up. We have a ton of questions over in the Q&A. I know some of your colleagues have been already answering them. So for some of you who've asked questions, you might want to just check the question and see if there's an answer. Do you want to take some of those questions?
No.
And the only reason I'm mentioning this is we have to be a little bit conscious on time, because we had so many questions early on. We're thinking maybe we shouldn't take the break, and instead we just kind of continue through.
Okay, yeah. Okay, yeah, let's do that.
How do you want to, do some of these questions? Is there anything in particular?
So there are some questions that I think I already replied, so they've already been answered. So yeah, I will keep it then. I will go through the workshop to make sure that we are on time, because
That's good.
Yeah.
Very cool.
I want to make sure we cover all the materials. Thanks, Anna.
No problem.
So let's go through our factors example, and let's make sure that you can see it. So here we have two codes. One is the guest program. This is what you want to run on the ZKVM, and the host. This is like prover on the host that will be sending your input data to the prover and will actually run the proof. So on this program, this is a factors program. So what we're actually doing, we send two integers to the guest as a input data, and then we run the prover. We generate the receipt, and we get the receipt back from the prover, and we print the number output from this journal. And when we run the prover, we actually go into this method guest program, and here we read two integers. This is A and B, and then we multiply it and we commit the product. So, and this is product. This is what we commit to the journal. So let's look closely into the guest program. So first of all, when you write a program, a guest program, you need to import like functions that need to be for interacting with the host environment. So this is done through RISC Zero ZKVM guest environmental variable, and then we need to read the objects from the host. We need to read the data. And then we need to also commit through this environmental guest environment to the journal. We commit product that we computed. And so please know that whatever you commit to the journal is a public. So be careful what information you want to commit. And then on the host side, on the prover, you pick like 2 random numbers, then you set up the execute environment, and this execute environment holds configuration details that inform how the guest environment is set up per the guest code execution. So this is where you also send your input data for the program. Then you obtain default prover and approve the ELF binary and return a receipt through running prover prove ELF. And then this is where you actually run this guest program, and then you obtain the output from the journal through a receipt journal, and then you can print the output and also verify the integrity of this receipt with the image ID. So this is how we the whole ZKVM works. You just in the guest program, you have the guest. This is the program that you will run on ZKVM, and the prover that will be sending the data to your guest, and will run your guest program through the prover, and then you can get back receipt and receipt content journal. This is your public output. So since we are a bit running out of time, I will so let me know if you want to have like a quick start with ZKVM, and otherwise we go quickly to the Bonsai and start our presentation about Bonsai. Mm-hmm.
Good. Thank you. Are you doing this one, or is this where we're bringing up your colleague?
So I will give a bit of like overview of Bonsai, and then this is where my colleague will get on stage. So,
Okay.
But since we're a bit like running out of time, I want to make sure that we go through whole materials. And if so, can people say if they would be interested to run ZKVM, generate a project and run it locally? Mm-hmm.
I think there's a few people that are. One other thing, Iryna, if you wanted, we can always have you jump back. Like for us, the only sort of cutoff is at the 55 mark so that we can announce the puzzle. But afterwards, if you wanted to jump back on and sort of do any additional stuff, you're welcome to do that. Okay. Let me then go quickly through this ZKVM, like quick start. Okay. And go to Bonsai, and then I'm just like, Hans, you're gonna have a bit less time to present. Okay. So guys, come please here on this dev RISC Zero API ZKVM quick start, and I will share my different page with the quick start. This is what you get when you run it. And let me just reshare it. Window. I'll share the whole window. So you can see it, right? So when you scan this code, this is what you get, right? So this is quick start. I will also copy and paste it in the chat. So this is a very easy and very fast way to get started with a RISC Zero. So let's first start with installing RISC Zero toolchain. Open also toolchain. So
just copy like cargo install, cargo install. And then, oops, sorry. And then let's do cargo install cargo RISC Zero. Okay, easier to copy. So you have some warnings, which is fine. And then cargo RISC Zero install. So, but before that, please make sure that you have installed Rust on your computer. There is a link here that lets you to goes directly to the Rust. And then let's create a new project. So to create a new project, we use our RISC Zero tool, and we need to pass basically two names. One is the new project name of the project, and another guest name. Guest name is a name of this program that you're running. So let me copy this. And run it here. So this cargo RISC Zero now created a template for us, created a project template for us. So if you check, unless you have this my project that's been created, so I'll go inside my project and create a couple of directories and methods, and it's already runnable. So if you go through this tutorial, you can see that how the share, how you share data between host and guest. This is what we just showed you, how the host prover send the data to the guest and how guest read it, and then how guest shares the results and generates the receipt. So in order to do this, let's see how our project. So this is the project that we just created. So we have host, and this is our host has, so this template by default has like one parameter, one integer that's been sent through execute environment to the guest. And then this is a prover that we obtain, and then we run, prover runs, proves and validates the computations, guest computations. And let's look at the guest. So here guest, we have, this is the guest in methods guest source main. And so this is like very simple to make sure that you guys all like running it. So it get back, it commits back the same data. And if you open on the main again, the output is here. It reads receipt journal, and then you can verify, and you can also run. So let's print one line to make sure that we actually run it correctly, that it's actually it gets the data. So this is output from guest. Save it, don't forget to save it. And then let's see how we can run it. So we run it through this cargo run release, and we set developer mode to 1. So this means that during the development of your program, we recommend first to start with developer mode, so it doesn't take quite a lot of time to actually generate zero knowledge proof each time. It sends like a dummy receipt, but then when you're actually ready, when you run the tests, everything, all your Rust is ready, Rust code, then set RISC dev to 1, and you just like see that it takes a bit longer to run. So I will do. So I will do in developer mode. Then you can see that for real proof generation, it just takes, you just set this environment variable to 0. So it's like almost ready, almost done. How are you guys doing? Does any of you have any problems while running this this program? So dev mode 1 is actually just making sure that the actual ZK snark proof is not generated. So it runs the program, but it doesn't generate this proof. So every time, so this is good during like development, right? So when you ready to run your when you're actually ready to run your Rust code, when you're actually ready to generate receipt to generate a proof, then you set dev mode to 0. And you start, it will just like take a bit longer to generate the proof. So that's why for this demo, I'm running with developer mode. And it's already a bit slow. I'm sorry, usually it's like my laptop is a bit slow. So while it's running, let's go and let's go and look through Bonsai, and then come back and check. So
actually, Iryna, just one quick, I just want to update you. Behind the scenes, we've made the decision that you have like another 4 minutes, and then we're going to take a break, do our launch of puzzle F2, and then Hans is going to come on after.
Okay.
Are you okay with that?
Yes.
It's just because it's 4 minutes. I think it would be too short.
Yeah.
And we really don't mind after. We just want to stick to the time in our schedule of the launch.
Okay. Yeah, thanks.
Perfect. Okay, so I'll be back in about 4 minutes.
Okay. So what happens if you don't want to run the ZKVM locally? This is one of the questions that people ask. So is there a remote option? And yes, there is one. There is a Bonsai. Bonsai is ZK proven as a service. So this is where you just like send your guest program to the service, and it generates it for you, and it's validated for you and generates a zero knowledge proof for you. So we provide the whole infrastructure, and this is ideal for like very heavy computations and for very fast proving. So, and thankfully to continuations that we have, now we can provide these services. So you can play with it locally, but it doesn't generate the proofs. If you really want to do generate the proofs, please use this QR code and please apply for Bonsai API keys. And the most exciting part that you can also do like off-chain computations. So let's look at the Bonsai architecture. So there is two ways of calling Bonsai. So what with Bonsai you do, you just like send your Rust code that you want to run on Bonsai. You don't need to worry about host anymore. So with this Bonsai, or you can send requests off-chain. So how you do it, you send a request to Bonsai Relay REST API. So this is through off-chain, this is through here. Or you can call request callback on Bonsai Relay contract through your user contract, through your Ethereum contract or any contract. So Bonsai Relay, what it does, it sends the proof request to the Bonsai proving service, and we run the program off-chain, and then we prove that your code was executed, and we generate the proof. We generate like snark proof, and we send it back to Bonsai Relay contract. So Bonsai Relay contracts verify the receipt, and then it starts journal from verify receipt, and then send journal image ID in a callback to your application contract. And yeah, so what's possible after you hear Hans presenting Bonsai Pay. And that's it from me for now.
Yeah, I'll share my screen, and then we'll just go over pretty quickly. Generally, this is kind of focused on like how do you go about thinking about zero knowledge applications in a general purpose sort of manner. So before, like, you need to write circuits. It's kind of complex. It's not a trivial process, and it really limits like what you can actually write with your programs. But now that we have this general purpose VM that can have verifiable computation just about anywhere, you really unlock this whole world of application development and ways to sort of incorporate zero knowledge into generalized programs, whether it's on-chain or off-chain. So today we're just going to kind of talk about like the sort of theory that you should go about thinking about how to apply ZK to existing problems. And we're going to go over a specific problem that we solved and demoed with this application called Bonsai Pay. So zero applications, yep, many applications could benefit from zero knowledge for privacy, security, interoperability. We all know that. That's why we're here. They're really useful when zero knowledge is really useful when you just want to minimize trust, right? You have verifiable computation. You can write programs that are verifiable anywhere. So you can run it on sort of a trustless setup. Any machine that's sort of executing this binary, these ELF binaries, is, it's a trustless machine. You don't have to trust it. And general purpose zero knowledge sort of enables novel application development. And we'll see that in a second. So wait till the end to see a demo, and we'll just go through a quick video demo. But I'm just going to go over some high-level theory. And we're going to start with probably the most boring and annoying topic for a lot of developers, and that is like authentication. It's sort of a meme at this point that authentication is difficult. It's a pain in the butt, and it's really easy to screw up. And that's still the case. This actually doesn't solve anything. Zero knowledge does not intrinsically imply sort of security or privacy, right? Like you have to think about these things very carefully, and you have to think about your problem sets very carefully in order to develop any sort of reasonable program in a secure way, right? So let's talk about OAuth 2 and OpenID. So what is OAuth 2? OAuth 2 is sort of the pattern that you see on the internet, widely used in Web 2 to log in, right? Sign in with Google, sign in with Apple, etc. But there's another layer on top of OAuth 2 that a lot of applications have sort of centered around, and that's this idea of OpenID Connect. OpenID is this sort of protocol that exists on OAuth 2. Basically, it defines a set of fields that allow providers to sort of provide identity or other sort of information in a compact and succinct form that is verifiable using public key cryptography. So this is, you see this all the time, whether it's sign in with Google or Microsoft or Apple or Amazon or Twitch or whatever. A lot of people incorporate OpenID on top of OAuth. It enables clients to verify the identity. So essentially, you get a payload from like Amazon or Apple or Google, and they sign this little payload. And you can verify that by looking at their public key. So they hold a secret key, they sign some payload, send it over to a web application or some other application, and you can verify that. And that's really cool and stuff. So typically this flow looks like signing with Google. It makes a request to Google. We get back an access code. This is why it's so easy to screw up. There's a lot of steps here, but you make a request to Google, you get back an access code, you make another post request to Google, and you say, hey, I want some sort of token. I want to get that identity of the person that just signed in. So you make another post request, and then you get back this horrible looking string. But really, this is just an encoded sort of payload with a signature. So we see 3 different color sections in this large payload. First section is the header, second section is the actual payload, and the third section is the signature that you can use to verify. And this generally just kind of looks like this. So you have this like signature, in this case it's RS-256 signature, so RSA. Not going to talk about RSA or the pros and cons of it or the security implications of the internet relying on RSA. That's for another time. It just exists, and it's the backbone of the internet. And then you get this payload in the green that sort of corresponds to this encoded payload. That's really cool. That's great and all. Thanks for showing me OAuth, Hans. That's really useful. This is a ZK hack. But what can we do with that? So now that we have this general purpose machine, is there anything that we can actually do to use login and traditional authentication protocols and enable that with ZK in maybe like on-chain applications or other sort of verifiable computation sort of processes that you need? Well, yeah, it matters because it's well established, right? Enabling traditional auth on-chain would be a huge UX improvement. And, turns out we can, thanks to this awesome paper that was just put out last year called OpenPubKey. It's called Augmenting OpenID Connect with User-Held Signing Keys. Some very clever people were like, hey, what if we just like put a user signable key inside of this payload? Then that sort of tightly couples these two things. And, we thought, well, user-held signing keys are basically Ethereum, right? Like you have a public key and then you have your private key and you can do things with that, right? So what if instead of using this like sort of, very niche kind of public signing key, and we actually just used Ethereum addresses with that? So what do? We kind of hack OpenID Connect in a way. Oh, I'm getting some stuff. 10 and 10. Sorry, I'm getting a cool. Yeah, cool. We do this technique called nonce hacking and packing, or that's the term that I like to use. Why do we call it that? Well, if we take a look, I just did that. If we take a look at the previous slides, we can see that we make these requests to like Google or Amazon, right? But there's this field in here called a nonce, which is really a number only used once, right? We're only supposed to use it once. The server that's serving the authentication should be checking these nonces and make sure that like that nonce isn't being reused within the same sort of session. So process looks very similar, except in these requests, we sort of provide a custom nonce. In this case, we decided to go with the public key of your Ethereum account. So you can see this Ethereum address in yellow, the nonce. And we make these requests. So we get the access code back, we make another post request, and we get this JWT. This is a JSON web token, that long string of text, the header, payload, and signature. And it contains the nonce that we asked for. So this is really cool because it tightly couples their public key cryptography based on RSA or ECDSA, other sort of signature schemes, and it contains something that we asked for. In this case, a public key, which is your public key that you can go and sign messages with or make transactions on a blockchain with. And that's really important because it tightly couples these two systems, this Web 2 world and this Web 3. And that's really cool. That's really great and all. But it's not that useful for blockchains yet. So what do? Well, we validate this JSON web token inside of the ZKVM, which sounds like it should be a hugely complex thing because you'd have to write a custom RSA circuit and all of that, but not with RISC Zero because it's a generalized system. So we can use existing sort of tools and libraries to validate a JSON web token, which is standard practice in most authentication, right? Validating JSON web tokens is the bread and butter of the internet. And we can do that inside of the ZKVM with fairly trivial code. So, like I said, we validate the integrity of the JWT against the public providers or the provider's public keys. And that looks like this. So we have this JSON web token, right? This long string of horrible text that nobody likes to see. Then we have some public keys that Google or Amazon or Apple, they have on a well-known endpoint, right? They have these certificates, these signing certificates that they use to sign these JWTs, meaning that they have attested to the validity of that payload. And we just pass that in to the ZKVM. So we can see here with the little ELF, this would like correspond to what's inside of an ELF binary that is passed to the ZKVM. And we run this on the Bonsai proving service to expedite that process of proving. And we get back this awesome little receipt. It contains the seal, contains the digest of the actual payload itself, and it contains the journal and whatever we choose to write out. We choose to write out nonce. You should probably also write out the expiration and issue date because you can't do that inside of the VM. It's a virtual machine, and you'd have to trust the host if you want this sort of system clock. So you just don't do that. So you write it out for other people to check. But the important part is we pass out that nonce in the journal. That's public. And once again, this tightly couples these two systems. You say, "Oh, great, Hans, you have a seal now. You have a receipt." Well, that's cool. But like we mentioned earlier, you can validate this on chain. So we can do snark validation on chain. So we have this receipt. We throw it into a smart contract, and we use a verifier contract, a Groth16 verifier contract, and we just verify the payload that is signed. We verify this this seal that contains the proof of the validity of the JSON web token from the authentication protocol that we've logged in with. So we've essentially tied Web 2 and Web 3 together and enabled on-chain transactions to correspond to a given user who's logged in by tightly coupling these security models. Pass that into a Groth16 verifier. Ooh, it's so good. We can now do things on-chain using Web 2. That's crazy. The potential for UX improvement here is massive, whether it's smart contract wallets, identity verification, access control, etc. These are all, we have it's possible now. We can do it. It's the problem is solved. Thank you, RISC Zero. So here is like some horrible looking sort of sequence diagram of what you would do. You'd have this application, you sign in, blah, 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 get the token, validate the JWT, get the proof back, send it to Ethereum. Cool. We've enabled traditional web authentication on blockchains. That's kind of a big deal. We've tightly coupled the identity of the person by using their Ethereum address inside of that nonce. We've tightly coupled that to the identity from the identity provider. And we've essentially unlocked trustlessly verifiable authentication on blockchains, like I've said. It's a relatively simple architecture to actually implement. And we can see that with the demo at the end of this slide. But like I said, this enables a whole lot of things in blockchains, right? Traditional and familiar login methods for dApps. That's a huge one. If we want sort of UX improvements, which the blockchain world so desperately needs, this is probably a very viable path of doing that. So it works well with payments, wallets, account abstraction, if that's ever really adopted. You can do things like smart contract access control, right? Like sometimes you'll write a method in a smart contract that you say, oh, only the owner can do this, or only certain roles can do this. Well, now you can have a new access control method where it says only people that are logged in with Google can do this, or only people with this email address can do this, or this domain can do this, or this issuer can do this. It's also very important for identity verification. If you think of identity platforms, traditional identity platforms for KYC or something, like they still follow this pattern. In fact, there's OpenID providers that follow this pattern where we can sort of nunce pack and maybe make, say, an identity NFT, right? So there's tons of applications that we can do here. So with all of this, you know, what does this actually look like? Well, it looks like a traditional web application or dApp where you connect your wallet and you perform some action on chain using this proof. So what does this look like? Let's just watch a quick video of Bonsai Pay. It was a demo that we released a few months ago prior to Istanbul. It is now offline, but the repo is still available at github.com/RISC0/examples. You should be able to go fork that repo if you want. Keep in mind that there are still security implications about this, right? Like you need to carefully consider authentication and security when you do this. But for the most part, it looks like this. So we have this application. It exists on a website. You go connect your wallet, pretty standard. And then you have this field and you say, hey, I want to send money to, say, somebody else, somebody with this email address. In this case, it's myself. Pay attention to the connected wallet address. I'm going to send some ETH to them. And this is going to send some ETH to an escrow contract that only hansmrtn@gmail will be able to claim if he logs in. So now I've sent this ETH any second now. And we come back as, you know, Alice or something, some other user. And Alice has this email, hansmartin@gmail.com, goes and signs in, looks pretty standard. You sign in with Google. Hey, welcome, Hans Martin. Let's prove that you actually own that identity connected to that wallet. So now we're proving it. In reality, it takes a bit longer. It's about 10 million cycles. So that was sped up a little bit. But now we can use that proof to actually claim this ETH off of this contract, only identified by that email address, right? So only the person that can log in with that email address can claim this ETH. And that's generally what it looks like. So once again, this kind of opens up tons of possibilities for application development. You're no longer restricted by the engineering requirements or developer talent that you have to write complicated circuits for, say, RSA. I'm not sure if you'd even want to do that, but you can. And it's this new world of sort of generalizable ZK that just is immensely powerful in the broad space of things. So we're excited to see what, you know, developers and people like sort of use ZK systems for, because it's so generalizable. You know, there's so many novel applications that we can't even think of. But that's what I'd like to leave you with. Check out the repos, check out the docs, check out the READMEs. There's a ton of helpful info in there. Hit us up on Discord. We're there.
Awesome.
And it was a pleasure.
Very cool. Thank you, Hans. I think this event is about to shut down, so I wanted to just make sure that we get to say thank you. Thank you to the whole RISC Zero team for coming out. What a great workshop. Thanks to everyone on the questions. I know there's someone who's trying to work with one of your tools, is asking for some help in the chat. And by the way, for anyone in the chat, if you have further questions, head over to the ZK Hack Discord. There's a ZK Hack channel. There will be a lot of chat around puzzles and stuff, but I'm sure there's going to be some RISC Zero folks over there too who can direct you to the right channels. So yeah, thanks everybody for coming out. ZK Hack 4, session 2. It's a wrap. Cheers.